Alright, so our three types of mechanical energy are kinetic energy, of course, which is 1/2 mv squared. We've got gravitational potential energy, which is mgh, and we also have spring potential energy, 1/2 kx squared. Remember, the U stands for potential energy. These are just two types of potential energy. They're both stored energy. One is stored in a spring, one is stored due to the height relative to the Earth or planet. Mechanical is potential and kinetic together. Mechanical energy will always be conserved, meaning the total will always be the same unless there is work done on the system. So what I mean by work done is some outside force is applied over a distance. Which is, if you're like, where is she saying that? That comes from work can be found by FD or change in energy. So what this is saying is basically this statement right here, right? Your energy is going to stay the same, or it will change if there is work done when there is a force applied over a distance. And technically that force needs to be parallel to the distance. So if you have a force this way and distance this way, that's no work done. Right, the two ways to tell if work is positive or negative. So first, the force and the distance. If the force and the distance are in the same direction, so force, distance are the same direction, that's positive. If force and distance are opposite directions, then that's negative work. And then the other way is think about your change in energy. If you have a positive change in energy, that means you are increasing in energy. So the system gains energy, or the system loses energy. If you have a force distance graph, so if you have FD, almost certainly you are going to need to find the area under the curve, so the area, and what that area will represent is the force times the distance, which is the work or the change in energy. If a system is just talking about the cart only, then we're only talking about kinetic energy. If we're talking about the cart, then you're talking about kinetic. If you're including the Earth as well, then that will be gravitational potential energy. If it's talking about the cart, the spring, and the Earth, that is kinetic, spring potential, and gravitational potential. And dissipated means loses. So that's like energy lost is the energy dissipated. It doesn't actually disappear, right? It kind of spreads. Basically, we're gonna, in here, energy dissipated is like energy lost. All right, box starts with initial speed, slides from one platform to another. Friction and air resistance are negligible, which means I don't worry about them at all, can ignore. For the system, including the mass and the Earth, so that's kinetic and potential energy, what happens to the total mechanical energy? Well, if there's no friction or air resistance, then the total energy, kT and potential, is going to remain the same, because there's no work done. If there's friction that is not negligible, so if I do have friction, then this total energy, so the total energy, mechanical energy, will be decreasing, because there will be negative work by friction. Let's go back to the no friction scenario. What if I'm talking about just the mass, like just this box right here and not the Earth? So that is saying just kinetic, not potential at all. What happens to the mechanical energy of just the box? Well, that's just kinetic. So the kinetic energy is going to be getting faster here and getting slower here. So your kinetic energy will increase then decrease, because you're going to be losing potential, gaining kinetic, and then gaining potential, losing kinetic. Whereas here, right, the two together, it stays the same. This one I'm just talking about the kinetic, so that will be increasing then decreasing. Here I've got two masses, frictionless, massless pulley. What is the change in UG and the change in kinetic? Release from rest and fall in 4 meters. So this one is going to go up 4 meters, this one's going to go down 4 meters. I know it starts from rest and then it moves, so I know for sure that you are going to gain kinetic energy, because at first you're not moving and then you are, so you got faster. So I can cross off this one, and this one, because I know I gained kinetic energy. It says that it's frictionless. We're talking about I guess it didn't say what system, but I meant the whole system, the two-block system. So for the whole system, then energy will be conserved. So if I gain 10 joules of kinetic, that must mean I lost 10 joules of potential. So that is how I know my answer is D without having to do any of the math. Now that one, right, I actually got kind of lucky because there was only one scenario where this one gained and this one lost. If I needed to get the actual number without just process of elimination, then of course we can do the math. So I can find the change of potential of the first guy and change of potential of the second guy. So change of potential is just going to be the mg, change in the height. Mass is 0.5, g, change in height, this one goes up 4 meters. Whereas this guy has a mass of 0.75 g and goes down 4 meters. So then you put that in your calculator. This is negative 30 joules. This one is positive 20 joules. So if this one gains 20 joules, but this one loses 20, then overall that loses 10 joules of potential. So loses 10 joules of potential. That energy doesn't disappear. It means it must go into kinetic. So positive 10 kinetic. Right here, release from rest. At point C, we know the speed is 6. Find the work done by friction. So this is energy not conserved. Work is just going to be the change in energy, which is energy at C minus energy at A. So I found the energy at each. You can put it into your equation. I just found it separately. It doesn't matter. At A, it was all potential, mgh, so at 10, 10, 5. At C, it was a little bit of potential and some kinetic. And 10, 10, height of 2, 1/2, 10, velocity was 6 squared. So then this guy has 500 joules to start with, and at the end we have a total energy of 380 joules. So then the work done is just final minus initial, so the 380 minus 500. So the work done by friction is negative 120 joules. And it makes sense that it's negative because friction is always opposing the motion, so F and D will be opposite, and also I'm losing energy, so it should be negative work. Alright, 300 meter high skyscraper. This is thrown down with an initial speed of 20, and then it hits the ground with the speed of 60. Energy lost to friction, so this is the change in energy, so energy at B minus energy at A. I'm going to call this my A and my B. A, you have potential and kinetic. So 2g, height of 300, 1/2 to 20 squared. At B, that is the speed it hits the ground with, so no height, so it's just kinetic. 1/2 to 60 squared. So this one is 3,600 joules, and I started with 6,400 joules. Oops, can't see. And then how much it changed. So that means I lost 2,800 joules. And then it says how much energy is lost. So that's D. If you're like, why isn't that negative? If I say I lost $5, I don't say I lost negative $5, right? The lost is telling me that it's a negative change. All right, here we've got frictionless water slides. So energy is conserved. This one is straight, this one is curved. What do we know about the speed at the bottom of the slide? So the speed right here and the speed right here. So I think through energy is going to be conserved. This one starts with mgh of potential, same here. All that potential is going to be transferred into the kinetic, which means they'll have the same kinetic at the end, so they should have the same velocity. Now if you're like, wait, this one has more mass, right? Whichever one has more mass, think about it. You've got mgh goes to 1/2 mv squared. The m's are going to cancel out, so it doesn't matter. They're going to have the same velocity at the end because energy will be conserved. Now they will not have the same velocity overall. Slide 2 is going to be faster first, so then it'll have a faster speed overall. So slide 2 will hit the ground first because it has a faster speed overall. No friction, so energy conserved, no work done by the motor, it's just coasting. What is the speed at point Y? This is point Y, by the way, it got cut off. So then I have mgh plus 1/2 mv naught squared, goes to, this is ke and potential, this one is just ke, goes to 1/2 mv squared. This is what I'm looking for, cross off your m. multiply by 2. When you multiply by 2, this half goes away, this half goes away, and this one gets a 2. And then last step, square root. See? Alright, we've got a mass of 0.05, velocity of 10 on a horizontal surface. It collides with the spring and comes to rest when the spring is compressed. So this is all kinetic, and it will be going to all potential once it stops. We've got the spring constant K. This is my mass. This is the initial velocity. It compresses 20 centimeters. We do not like centimeters in here, so your x is 20 centimeters, but we need to convert that into meters. So divide by 100, that's 0.2 meters. And now I need to find what happens to the energy. So normally I would assume that energy is conserved. It didn't specifically say frictionless. It didn't say anything. It's actually asking about energy. I've been given the numbers, so let's just check it out. My energy at the beginning is kinetic, 1/2 0.05 10 squared, and that gives me 2.5 joules. At the end, it comes to rest, so it's all spring potential. So 1/2 kx squared, k is 100, x is 0.2 squared. When you put this in, you get 2 joules. So if I had this much kinetic, it went to all, it should have gone into all potential, but I only have this much potential. That means I must have lost 0.5 joules along the way. Because I'm including the whole system, right? The block and the spring and the earth. So the system decreased by 0.5 joules. So that would be like energy dissipated, whether to friction or something else, I don't know. Fall falls from the top of the building through the air. How does the kinetic compare to the potential at the top? So it was all potential, and then here your potential is 0, and you're asking how does the kinetic? And normally that would be the exact same, but I'm pretty sure, yeah, air friction or air resistance is present, which means you're going to lose energy. So my final energy is going to be less than before, so K is going to be less than U. Here we've got a spring, compressed to distance D. I did it. I put the D here, but then I didn't have D in my answer choices. Classic. When the block is released from frictionless ramp, so energy is going to be conserved. What is the kinetic energy at the height? So let's think about here it's all spring, here it is potential and kinetic. So then I've got US equals UG plus kinetic. To get the kinetic at the top, I would just subtract over. So that's 1/2 kd squared minus mgh. So C. And then this should make sense because I have this much energy. Here it's being shared between them, so it doesn't go to all kinetic, it goes to some potential. So whatever amount that didn't go to potential is going to kinetic. So the amount that I started with minus what went to potential is how much kinetic I'll have here. Person lifts a box from the ground to a table at a constant speed. So constant speed means you're getting the same kinetic energy. How does the total mechanical energy of the Earth box system? So that means I'm talking about UG and kinetic together. I know the kinetic stays the same, but this is lifting up, so that would be gaining UG. So if I'm gaining UG and keeping the same, that means overall you're gaining energy. So, and the total mechanical energy is because positive work. Oh yeah, I meant to cross off C here. But it's okay because increasing doing positive work. The other way to think about it is the person is pushing up and the displacement is up. So then these two are in the same direction. That's positive work. And when you do positive work, you are going to gain energy. Two ramps, both same height. They both have the same coefficient of friction, which is mu. That does not mean they have the same force of friction. That's different. How does the change of potential and kinetic compare? So from here to here, the change of potential is mgh. From here to here, the change of potential is still mgh. So they should have the same change in potential energy as long as they're reaching the bottom. But they will not have the same kinetic because energy is not conserved here. If you look at these, one of these is going to lose more energy than the other. So this one has more work done by force of friction. Oops. for two reasons, because it has a greater force of friction, because mu Fn is the force of friction, and they have the same mu, but this one will have a greater Fn, and also this is just a greater distance traveled, and work is Ft. So this one has more work done, which means it loses more energy, which means it'll have less kinetic at the bottom. This guy will not have all of the kinetic as potential, right? This one still will lose more potential than it gained, but compared to this guy, it's going to gain more than this guy does. So this one will have a greater change in kinetic. This one will be going faster at the end because this one will slow down more with more work done. So this one will gain more kinetic. And one will reach the bottom first because it is steeper, and also with the friction, it's losing less velocity due to friction. 30 meters skyscraper is thrown dropped, okay? That's supposed to be dropped. 100 joules of energy is dissipated, so I'm going to lose 100 joules. And what will the velocity be at the ground? So I'm going to start. This is going to be my A. This is going to be my B. The energy at A is just the potential, mgh, to G300, not 300. This is 600 joules. So I have 600 joules. And at the bottom, this is going to be all kinetic. But it's not going to be 600 joules because I'm going to lose 100 joules of energy on the way. So this is going to be equal to 500. So then 1/2 2v squared equals 500. Square root v square root of 500, which is, don't know, 22.36. Other way to do this is, some of you like to do your equation. So your change in energy, the negative 100, would be the energy at A. No, B minus the energy at A, right? Final minus initial. Energy at A is the mgh. This is the 1/2 mv squared equals negative 100. And then you just plug in or rearrange for B. Either way, you're doing the exact same process. One is kind of thinking through it. One is like along the way. This one is thinking through and then just plugging in. 13 starts from rest. A force is applied. The force as a function of the displacement. In a final speed is this at the end of the 0.1 meters. What's the mass? This is a force distance graph, so almost surely I should find the area, which represents the work. So my area is just going to be the work. This is a triangle, so base times height over 2, so that's 0.1 times height of 20 over 2, so that just gives me 1. So the work done is 1 joule. Now this work is also the change in energy. So this one, it's talking about it starting from rest and acquiring a speed. So this is the change in kinetic energy. So one is my change in kinetic energy, which is K final minus K initial. And it started from rest, so I know my initial kinetic energy was 0. So my final kinetic energy is this, so 1/2 mv final squared, which v final was 2.4 squared. And then that is a number. This is 2.88 m. Divide over, you get a mass of 0.35 kilograms. So key thing there, my area represents my work done. My work done is just the change in the energy. And then once I have my change in the energy, that's just my change in kinetic, and then plug in from there. This has a height h, length L, that's supposed to be an O. It has a velocity V at the end. There is force of friction, so energy not conserved here. I'm trying to find the force of friction based on these three things. So I'm thinking energy not conserved. Let's do work. This says rough ramp. So work is the change in energy, which would be energy at B minus energy at A. Energy at B is just the kinetic energy, the 1/2 mv squared. And then A is just the potential, the mgh. Now I'm asked to find the force, but remember work is also equal to the Fd, so this is the force of friction times the displacement. The distance traveled, right, the part of the displacement in the direction of the, or opposite direction, I guess, of the friction force is L. So then all I have to do to get F is divide by L. So I found my work, right, and then work equals Fd, divide the distance over. We've got a 1 kilogram block attached to an uncompressed